So I'd just like to begin by, sorry about that, thanking the IMF for allowing me as an outsider to the mount-making community to come here and present some of my research. So today we'll be talking about some of the more details of the testing that was conducted both at UCSD as well as at the Asian Art Museum. So all of the research that I'm talking about today has really been scoped and been based on a large NSF, or National Science Foundation, grant under the IGERT program specifically for cultural heritage diagnostics. However, all of my specific research has really been targeted towards the seismic response of statue-pedestal systems. And in this effort, I've really been able to touch into 4 distinct research phases, and I will do my best to give a brief overview of all 4 of these categories, but would be more than happy to talk individually with some more detail on some of these categories. So the first phase of research that I'll present is really a field survey. So coming in as engineers, what exactly is a mount? What types of mounts can we expect? What types of geometries of the statues are we going to be dealing with? And that type of information can then help us to design experimentation whereby we want to measure the physical response of statues or statue-like systems to the different kinds of earthquake demands. And then the results of this can then help to guide the development of predictive computer models, such that we can then simulate the response to an individual earthquake, as well as just to gain additional information and insight into how they respond as a system. And then ultimately, all 3 of the previous research phases can then help to guide seismic mitigation once vulnerable configurations and systems have been identified. So I'll first jump into this first phase, which is the field survey. And so the primary goal of this research phase is really to record the complex geometry and mounting conditions that we might encounter in the field. And so as an engineer, I can broadly classify statues and statue systems into 2 main categories, namely freestanding and, well, mounted in general. Obviously, there's a variety of types of mounts and subcategories there. Where freestanding, I simply mean any statue that is subject really only to gravity and friction. There's no anchorage, bolts, or epoxies. They're just kind of hoping that it stays there. Whereas for the mounts, in terms of the mounts that I'll go through today, we'll just very briefly, of course, go over some of these mounts in terms of the type of the restraint, as well as the location of the restraint, relative to potential motion of the individual statues. So the first case that I'll present is this mount that Vincent previously discussed regarding these Colossi sculptures at the Asian Art Museum. So as we can see here, there's this steel post system, and the statue is supported vertically based on this molded foot, and then it's restrained laterally using these fitted arms and the compression felt pads. And this is in contrast to other statues that were surveyed from the primary galleries of the museum for comparison. So what's shown here is, again, another very large statue. However, it is mounted simply by placing the contoured base of the statue into a fitted concrete block. And this contrasts to the Colossi sculptures because all of this restraint now is essentially lumped at the base, both vertically and horizontally. Another example that I'll compare and contrast to, now while this is not necessarily a colossal sculpture and it's not actually stone, we can still use it for comparison. And this is restrained or mounted using these contoured bracket clips only at the base. And the final sculpture that I'll go through with regard to the mount is another very large colossal sculpture, a bodhisattva. And this is restrained using an epoxied anchored bolt, or an epoxied anchor, which is within the center of the statue, and is then restrained laterally using a turnbuckle beneath the pedestal of the individual statue. And now, while all of this manual recording of all of the different types of restraints was conducted, in order to capture the geometry of these individual statues, it's fairly apparent that my tape measure really isn't going to give us very accurate geometry. And so to combat that, laser scanning or light detection and ranging technology was incorporated. What this gives us is essentially something called a 3-dimensional point cloud, or a set of vertices that describe the surface. And so specifically, what is LiDAR? It's an active remote sensing technology, and it is a handheld unit. We place it on a tripod, and it emits laser light. And it's then reflected, as shown in the GIF on the right-hand side, by obstacles in its path. And then the distance to that object is then calculated based upon either the time of flight of the laser pulse or based upon a phase shift of a continuous wave of laser light. The specific unit that was used in this study was capable of acquiring nearly 1 million points per second at about millimeter accuracy. And now, as this was a line of sight technology, multiple scans of the target are needed such that we can get the front, back, and minimize all of this occlusion. So then all these individual point clouds had to be unified into a single point cloud, as shown here in the rotating video. But again, this just gives us points. And in order to do computer analyses, we really needed to be more of a digital reconstruction or a surface. And so to do that, a Poisson surface reconstruction is able to give us this watertight, fully enclosed, three-dimensional surface mesh for integration into numerical models. And so with these now digital records and surveying of the initial mounts, we can then try to determine how they will respond to a given earthquake through experimentation. So now the primary goal of this phase of experimentation is to determine those natural frequencies, not just for the statue, but for this whole statue-pedestal mount system as a truly installed system. And so just as a reminder, so all structures, remember, they have their natural frequencies that they want to vibrate in. And why we want to know these is for this problem of resonance. So this little red dot up here is moving just a small amount of distance, but it's doing so very close to the natural frequency of this mass spring system, which can then lead to resonance or excessive motion. And now, by looking through a museum, we don't necessarily always see mass spring systems. However, this statue-pedestal mount system really forms all together a mass spring type of a system. So it's easier for an engineer to see, but just bear with me. So in order to measure these natural frequencies, a process called experimental modal analysis can be conducted. And this is typically done for structures, bridges, buildings, as well as electrical transformers. But here is the specific target for statue-pedestal systems. And so in order to do this, the acceleration is measured at multiple locations along the statue as well as along these restraint-type systems. And now all of these individual accelerometers, while on a typical structure we might want to drill them in and really secure them for obvious reasons, we secured them with a rubber band to get them as tight as possible to the individual sculpture. However, a polyethylene wrap was used beneath that rubber band to reduce any particulate transfer. And however, when we were dealing with the modern steel post system, we're able to use a magnetic contact, which is simply much easier to install and gives a nice firm contact. And now, while everything is, vibrating in everyday life, it makes it very difficult to process the results if we're using just its natural day-to-day vibration. And so to combat that, we use a really simple, small force transducer just to give it a little bit of vibration, a little bit of excitation, such that we can increase the signal-to-noise ratio of the accelerometer's responses. And all of this system, as shown, fully constructed here, being imparted in excitation, is controlled via a laptop. So it's a very portable type of a system, and that we can look at the results in real time. Now, while yes, we can look at the acceleration over time, that doesn't really give us that much exciting information. We're trying to figure out natural frequencies, so it makes sense to look at the results in the frequency domain or through a process called a fast Fourier transform of the acceleration data. And now what this indicates is the peaks then correspond to a heavy presence of that frequency in that acceleration time history. So what we see here, these are some sample results for the Colossi 112 statue, and there are two distinct peaks. And these identify two of the lowest natural frequencies of this statue, restraint, and pedestal type of a system. And now if we take a look at how all of the surveyed statues compared, we see that these Colossi statues were really quite low in comparison to some of the primary gallery statues and their statue restraint systems. As a matter of fact, if we consider the notion that the term rigid is typically used to describe structures with frequencies in excess of 16.67 hertz. What we can see is these colossi are really quite flexibly attached, which is not necessarily a good thing considering all of these statues in a base-isolated building. We want them rigidly attached. So there's really two main options that we can do with that now. We can either look at isolation, or we can look at how we can modify that type of a restraint to make it more rigid. However, to gain a little bit more insight into what these results of the experimental modal analysis were really giving us, computer simulations or modeling can be incorporated. So the results of that LiDAR, that three-dimensional mesh that was developed, can be directly incorporated into a finite element analysis. This is a typical engineering method or process that can usually give us the distribution of stresses on a given structural component. So this used the input, so highly accurate geometry from the individual meshes, as well as assumed material properties where this was either sandstone, marble, etc., and then assumed boundary conditions where these boundary conditions are really representing the type of mount. And now for a worst case comparison or a really truly rigidly attached body, we went ahead and fixed all of the base of this statue. And what we see here is this is the first bending mode of the actual statue. And we see that its frequency is 39 hertz. So that's a lot bigger than the ones we were recording. The first bending mode in the transverse direction, 52 hertz. And the torsional mode is actually 171 hertz. So what this is indicating is that all of these measured frequencies from the experimental modal analysis are truly system-wide properties and a function of how the system, the pedestal, and this mount system are interacting together as a system. With this, we can then actually try to look at how can we use this now understanding of the natural frequencies to predict how it might respond in the actual museum building. So what's shown here on the right is a decently cluttered plot, but I'll do my best to explain it. So along the horizontal axis, this is the frequency. And then along the y-axis are essentially amplification on the right y, as well as an effective acceleration along the left axis. And this is a function of the building. So as Vincent had mentioned, the natural frequency of the building shifted to around 2.4 seconds. So that's what this big hump is indicating. You can think of it as a quasi-frequency domain analysis of the building's response. However, because it's not a perfectly rectangular building, there are other modes that would be excited, which is this small hump that we see down here. And now what we can do is we can overlay the natural frequencies of the statue systems onto the building. And what we see with these blue lines here is that the primary gallery statues are effectively rigidly attached to this building. There isn't going to be any amplification, you can see by this one over here, there won't be any amplification due to vibration of that mounted statue system. However, for these colossi statues, what we see is that they lie in this region where there's actually quite a significant hump. So what this means is that if the building is shaking and it's experiencing around 0.3 Gs or so, these statue systems, these colossi statues, might actually be subject to an effective acceleration of almost 2.3 to 2.7 times that amount. So again, this really emphasizes that we can attempt to shift their natural frequencies and make them more rigidly attached, or we should really begin to look at what we can do to mitigate these effects in a different way through base isolation. So with that, I'll just jump into the mitigation. So now, most component level base isolations attempt to shift the frequency of a component. However, when we're dealing with this in a base isolated building, a lot of those techniques don't really apply anymore, and it makes it very difficult. So a very simple solution to that that was proposed by EQX is to essentially create a very slick sliding plane. So rather than shaking and vibrating, just have it slide during a motion, and that'll cut the forces transmitted to the statue by whatever that coefficient of friction is, which by the polymer that they installed is about 2%. And these are the shop drawings that really show the actual implemented base isolation system and its incorporation into the actual pedestal. And what we can see here is just how smooth of an interface this actually is, where this is this pedestal box, And then we have that smooth interface along the bottom, so just a quick push and it slides. Or an earthquake shakes, and all it does is a little bit of sliding. And now, in addition to this experimental modal analysis, we're also able to incorporate the concept of these sliding isolators into some ongoing shake table experiments. And this blue tower is what I like to call my statue-like structure, and I'd be happy to explain why it's most like a statue after this, perhaps. And this is a statue on top of a pedestal, and here we have this on top of a high-friction interface compared to this low-friction sliding interface. And what we can see is really this reduction in terms of the quite significant motion of the statue atop this pedestal, and rather it becomes all lumped at the base. In addition, a test was conducted where this statue-like structure was restrained or mounted atop this pedestal. And what we can see is all of this motion really being concentrated at this base. So we see fairly significant sliding of this body rather than significant motion and forces being transmitted to the pedestal and to the actual sculpture. And so in conclusion, a variety of mounts and restraints exist for large sculpture, as I'm sure this audience is very well aware. Preliminary results of a very small sample indicate that certain mounts for these colossal sculptures can achieve rigidity a lot better than other types of mount systems. However, if the statue system, including this mount and pedestal, is anticipated to have a natural frequency close to that of the building, artifact-level base isolation is a viable option. Now, in today's presentation, sliding-based isolation is shown to reduce the demands on the actual statue. However, this is very much a case of being in a base-isolated building and for these specific statues, and there's really other methods of base isolation for these statues, as well as there's additional room for research into what the best types of isolation are for identified vulnerable configurations. Bulk of the funding for these experimental campaigns was from the National Science Foundation under an IGERT award, as well as an MRI award, with supplemental experimental funding from the Qualcomm Institute, Friends of CHISA 3 World Cultural Heritage Society. However, the experimental modal analysis that was really presented today was thanks to a very big collaboration with Mr. Vincent Avalos of the Asian Art Museum in San Francisco, the Museum Conservation Institute of the Smithsonian, EQX Global for the isolation systems, Farrell Elsesser for the response of the actual museum building, as well as the Kingdom of Saudi Arabia for allowing us the opportunity to work very closely with the Colossi sculptures. And with that, I'd like to thank you all for this opportunity and to thank you all for your attention.